So this unit is concerned, the most part, this part of the unit, with chemical and physical ways to control microbial growth. Pretty much disinfection, sterilization, the stuff that we talked about before. And I'm going to continue our conversation that we had last week with the whole idea of different biocontainment levels. So basically, BSL stands for biosafety level, and the greater number corresponds to more dangerous microorganisms. Now, I can promise you, question-wise, I have no intention of, telling you to do the risk assessment in the class and give you a biopathogen, give you characteristics, and then you're like, shit, is it BSL 1, 2, 3, or 4? Okay? So just general idea, have a general concept. So I'm going to highlight the keywords here. So for BSL 1, not known to cause disease, okay? That's it. For BSL 2, look at this. The word indigenous, what does that mean? It means that this microorganism can be locally found. Influenza, hepatitis C, SARS-CoV-2. For some reason I keep going with viruses, okay? Disease of varying severity. And when you look at moderate risk, it implies that there are either treatments or vaccines, or maybe both. So that would be, for example, influenza, biosafety level 2 pathogen. When we deal with BSL 3, it can be indigenous or exotic, and it can cause serious diseases. I wouldn't go as much potentially lethal. That's, what is the potential, right? Not necessarily only through respiratory transmission. This is why I tell you that I have no intention of asking you anything complicated here. Let me explain. For instance, SARS-CoV-2, the causative agent of COVID, is still classified as BSL-3. It was classified as BSL-3 in the very beginning because it was easily transmitted by respiratory route. And there was no specific treatment. Am I making sense? The disease can be lethal, don't get me wrong, but in majority of population it's not. Most people recover it, like if you look at the statistics. So the main issue was because it was very easily transmitted respiratory pathogen. On the other end of the spectrum for BSL-3 is the virus I worked with, yellow fever. It's not transmitted respiratory. It can kill you fairly easily, much easier than SARS-CoV-2, okay? And it is not indigenous. It's exotic. It's not present in the United States. But there are two factors that make it a BSL-3 pathogen. First is the vaccine, and second, it's really not easy to transmit. Okay? Obviously, BSL-4, anything that is exotic and super dangerous. Okay? Infections are frequently fatal, and treatment and vaccines are not really available. We're talking about hemorrhagic fevers, crime in Congo, Ebola, Marburg, Lassa. There are so many geographical names after which those diseases are named. Okay? So far makes sense? Go ahead.
So those won't be indigenous?
Oh, no. Any indigenous, I am not aware of an indigenous microorganism in the United States that would be categorized as biosafety level 4. Okay? That's a good question. No. Yeah, there are very few labs that are at this level. I worked at BSL-3 only. Violations of all the legal things. Most of them are felonies that are punishable by jail time. You have a question?
Yeah, in 4 they wear the big suit with the respirator. Did they do that in 3 also?
So in BSL-3 you wear a Tyvek suit and you wear a positive pressure helmet with a filtration unit strapped behind your back, which blows the sterile air around your head so nothing from the outside reaches your respiratory route. In BSL-4, you are in the full isolation suit with the external air being supplied into the suit. You're basically an astronaut. Okay? And there's a link on this slide, this one. I hope it still works. I didn't check it in a while. So this is the movie, actually, the documentary that was filmed in Biosafety Level 4 facility in Boston before this facility became hot.
I know.
Yeah. It's a pretty cool movie with a lot of interesting technical nerdy details about how this facility operates. Okay? So now we're going to talk about some fun stuff with Ebola, right? Easy segue. So, causative agent, enveloped virus, RNA genome. The family is called Filaviridae. You don't need to know that particular name because of the filamentous structure of the virus. Okay? So transmission, we can categorize two transmissions. Okay? Zoonotic from animals, probably bats, and then from person to person, contact. Okay, it can be blood, it can be bodily fluids, vomitus, diarrhea, sweat, saliva, anything like that. Make sense? And there were cases of sexual transmission, but they are very rare. No respiratory or fecal-oral route. Okay, and no transmission by vectors such as mosquitoes or ticks. Symptomatically, it's a hemorrhagic fever. Okay. Typical hemorrhagic fever, which means a systemic inflammation, which results in vasodilation and leakage of plasma into the tissues. So the person develops forgot the name for vasodilation shock. Cardiogenic, hypovolemic, whatever. So due to the low blood pressure and due to the hypovolemia, people usually develop shock. Okay? Am I making sense right now? So people die mostly if fluids are not supplied. It was shown that fluid supplementation together with antipyretics to fight the fever reduced mortality to about 10%, which is pretty good. Yeah, case fatality ratio is 50 to 90%, okay, which is a lot. But it's mostly because of the lack of proper medical care in the area. So the biggest outbreak so far, 2014-15, so you can see about slightly more than 30% mortality, case fatality ratio. But the reason for it is not that the virus is that deadly, but for the most part I would give this. Deteriorated public health, and WHO absolutely botched the international response. In the United States, there was an outbreak of Ebola virus in Western Virginia. Nobody got sick. Humans didn't get sick. Monkeys got sick a little bit. So, that's it. Cases in the United States in 2014-15, there were several of them. The first one was in Dallas. So the guy flew back from Liberia, went to the emergency room, lied that he was in contact with Ebola patient, came back next day in ambulance, died 2 days later, gave Ebola to 2 nurses. One of them flew from Dallas to Cleveland and back. Not a single person on any of the planes got infected. Ebola is ridiculously hard to transmit. They were cared for. They recovered fully. Everything was fine. And New York, there was a guy, he was a physician in affected area in Africa and came back, volunteered there. And he came back, had a fun day in New York with friends. Next day, felt a little sick. went to a physician diagnosed with Ebola. Nobody got sick. Among people who he hung out with. Medevacs, there were 3. One of them was unsuccessful, so the guy was flown to Omaha. He was too sick. She didn't make it. It was too late. And there were a couple of medevacs to Atlanta and to Frederick. So Atlanta is CDC. Frederick, Maryland is Walter Reed Research Institute. That's military. That's Army. And all people who got there were fine. Okay? So, outbreak of this disease isn't really possible in the States. It's hard to transmit, and we're super paranoid. Okay? It's much easier to avoid contact transmission than respiratory transmission. And it's not, like, I'm not trying to minimize it, but if you look at the causes of death in Africa, and it's 12 years ago, it has to be updated, but the order of magnitude is pretty much the same. So now it's not, for instance, 550,000 people who die of malaria, but about 470. Sorry, but that's still too many people, okay? And 11, 12, 15,000 people. Ebola does not represent a major public health concern. Does that make sense? So it was pretty much just, ignorance on our side that we blew it out of proportion. And we failed to address the real issues that can be addressed, like malaria, diarrhea, malnutrition, okay? Makes sense? We failed to address those things in those countries, but when stuff like Ebola happens, we all go completely mental about that. Like banning people from coming over, stupid stuff. Treatment. There are no specific drugs. There is an antibody, which is really good, really expensive. Nobody uses it because, the budgets of the countries where Ebola strikes, they can't afford it. Then there's a vaccine. It's really good. So as you can imagine, it was paid for because here's the deal. When you try to develop a vaccine, you have to consider how many people are going to take it. If companies that made SARS-CoV-2 vaccine, they get pretty good money. I'm not blaming them. It's fine. It's normal. If you will ask pharmaceutical company to develop Ebola vaccine, they will say no, because the market is really small. You're not going to vaccinate hundreds of millions of people against a disease that strikes occasionally in different locations. Make sense? It's economics. So farm companies weren't willing to pay for it, and there's one government agency. Huh?
U.S. Army did it, right?
General Pentagon. It was Army who ordered. They have shitload of money, so they asked people to do it, and they did it. And then when that happened, when the outbreak happened, they started deploying the vaccine. And I don't want to come across as heartless and cynical, but the problem with that deployment was it was closer to the end outbreak, and the number of cases was small, and it wasn't enough to fully assess the effectiveness of vaccine. So the data that we have show that it's good, but we need more data, and it sounds very cynical. Basically, we need more people to get Ebola to assess the vaccine, which is a conundrum that cannot be ethically resolved. Okay? That makes sense? Now, just an illustration, a few things that we're going to talk about later. Found some interesting data about the stability of the virus. And if you look at this in the water, it gets inactivated in a few days. So if somebody spat on the surface, and it's warm, it's like 27 Celsius, in 4 days the virus is gone. Okay? Now what I want to highlight is this. Once you start covering the virus in the drying blood, it survives longer. When you cover it in liquid blood, it survives even longer. Any bodily fluids or human excretions, from sweat and blood to vomitus and snot, have protective effects on pathogens, on microorganisms. Does that make sense? Good? In terms of the inactivation, interestingly, Ebola virus is very easy to destroy. You can see here that 67% ethanol, pretty much hand sanitizer, is sufficient. It activates it in a matter of minutes. Okay? And bleach is pretty good. It's got to be concentrated. I just checked the concentration of like household bleach today. I was curious. So household bleach is 6% hypochlorite. If you dilute it 6 times, it's 1%. And it's really active. Okay? So just consider this. What surprised me, though, is the survival of the virus on different surfaces. I was expecting a virus to be more protected on the material that is made out of natural fabric and kind of porous. But turns out cotton gowns, kind of deadly for Ebola virus. It doesn't survive. I don't know why. I have no explanation to that fact. It survives much better on plastic gowns, masks, and even stainless steel, but not in a cotton gown. That was a bit surprising. So my point here was to, first of all, illustrate the role of organic compounds, such as human excretions, on the survival, and highlight the differences between different antimicrobial chemicals. Now let's get to the boring stuff, which is sort of fundamentals. So first of all, this list of the most to least resistant structures, so endospores and prions are most resistant, and everything that's in here, list. Okay? Now, you need to know that. I will absolutely ask you to identify either the most or the least resistant from the list. Okay? Does that make sense? There will be questions like that. Endospores and prions, basically look at this. So this sign is like more, right? So we start with the most resistant and we end with the least. Sounds good? Decimal reduction time, absolutely know the meaning of it. It's a time to reduce the number of microorganisms 10 times. If you look at this illustration, in the span between 20 and 25 minutes of observation, so in 5 minutes, the reduction is 100 times, from 1 million to 100,000. So in this case, decimal reduction time is 5 minutes. Obviously, decimal reduction time is not a constant that is chiseled in stone, you know. It depends on many factors. And here's what I want you to process. If you have 2 methods, and one method offers you lower decimal reduction time, this method is more efficient. Am I clear? Because if you have 2 methods, you compare decimal reduction times between them. The method with the lower one, shorter one, means it's more efficient. It kills faster. And if you compare 2 microorganisms, then the organism with greater d-value is more resistant. Does that make sense? understand the definition of Seidel and static. Okay, so let's talk about physical methods of control first. Heat. Moist is better than dry, always. Okay? If you look at this particular line in this graph, D value for moist heat at 95 Celsius is 32 minutes. D value for dry heat at 95 Celsius is 615 hours, which is like a lot, you know. Definitions of these terms. I'm not gonna, that's pretty straightforward. No, just know the definition. Questions? Moving on? Cool, okay. So now we're gonna figure out what to do with that table. I'm gonna highlight what you need to know, and I'm gonna cross out things that you absolutely should know. So for every method, you need to know kind of examples. Let me actually write stuff down here. Okay. So level of control. It's annoying. Okay, level of control. Sterilization, disinfection. You see what I'm saying? General application. Okay. So what I mean by general application? What did I just do? Sorry. Okay. I probably closed one note, which is fine. A second. Okay, let's continue. General application. What do I mean by that? What would you use to sterilize surgical instruments? Okay, so first of all, you need to sterilize them, right? So you can choose either dry heat oven on incineration or autoclave. Technically, you can throw the scalpel into the fire, but it's not ideal. So that would be probably autoclave. Am I making sense right now? Yeah. There will be no questions about pressure-mediated methods. Okay? 100%, just none. And you don't need to know any of that stuff. I am not asking numbers. Okay? Am I clear? So you can expect questions such as, which of the following methods is sterilizing? Or, what would you use to, I don't know, disinfect, blah, blah, blah. So you can pick a method that provides at least a disinfection level. I also want to highlight that any cold-mediated methods are static. They're not Seidel, they can't kill, they just prevent the growth. And the last bit on that slide, remember, it's multiple choice. So I just want you to be familiar with the list and recognize those pathogens. This is pretty much the reason why we pass practice. Does that make sense? All good? Cool. Continuing, physical methods, radiation. Things to know. Ionizing sterilizes. Okay? Heat sensitive items, food sterilization. Okay? So basically gamma rays will be used the most. Convenient for food sterilization, it increases the shelf life of foods. Right? It's very actually useful for this. Non-ionizing radiation. So it is not that sporicidal. So I'm going to cross one statement out. Okay? Disinfection. Okay? Reasonable? Another application of the UV light is water treatment, and you all know hospitals and dental offices that use it for microbial control just on the walls, right? Good? Know the penetration ability here. Gamma rays are most penetrable, then we have X-rays, and the least penetrable are UV lights. Questions so far? All good? So filtration, liquid or gas. Okay, that's important. That's the only way you can reliably remove microorganisms from the gas. Heat is not required, which is also good, as you will see soon. So, HEPA filtration, air filtration. Question that you should ask, what level of control does it provide? Depends on how much money you have. And I can explain. So, finer filters are more expensive. Air handling for those filters is more expensive. So basically, if you are running a lab where you have to have air completely sterile, it's going to cost, but it's doable. Make sense? Okay, it depends on the level of cleanliness. Membrane filters for the fluid sterilization. You see them at these two illustrations here. Why use them if we can just throw that fluid into an autoclave? What if the components of your fluid are temperature sensitive? You can filter the fluid without affecting its chemical composition in any way, just removing the pathogens. Does that make sense? That's the big advantage of membrane filtration. Questions? So I want to emphasize again, you're going to get questions, which of the method is sterilizing, disinfecting. You can also totally expect questions addressing the application. Again, folks, you are not safety officers in the large hospital. Basically, I gave an example with the surgical instruments, right? Right? So imagine I'm telling you, you need to sterilize a hamburger. Okay? What would you use? What? Gamma rays, yeah. Because this is what I like about English language. It's the modality verbs. Can you autoclave a hamburger? Huh? Next time I'm going to bring it in and stick it in an autoclave. We're going to autoclave the hamburger. I'm going to ask permission. I'm going to see what's coming out. Can you eat the hamburger after autoclave? Follow the verbs. Can you? Oh, you can. You're not going to enjoy it. It's going to taste like crap, but you can eat it. It's not toxic. Okay, does that make sense? So my point is, You can do that, you can feed people with this crap, but if you want food to retain its food qualities, you're going to use gamma rays. Same way with surgical instruments. You can do dry heat oven at 300 degrees Celsius for overnight. It's going to work. Much simpler to throw it in the autoclave for 20 minutes. Okay? So, just considerations, and I'm not going to throw curveballs at you, I promise. Okay, chemical methods. There will be questions about the application of chemical methods, just like about applications of physical methods, okay? So when you think about those answers, consider this. So in other words, is it affordable? Is it toxic? Is it corrosive? Does it stain? For that particular application, it may be important. Okay? I'm not going to ask you about the tables, and unfortunately I don't have enough time to go over them. So for each chemical, you need to know what they are used for in general, what is their mechanism of action, and what level of control they can provide. Am I clear? I'm going to break it down on the halogens. I'm going to go slow, and then we're just going to kind of speed it up a little bit as we move farther. So first, halogens. Which halogens are used? Chlorine iodide. What is the mechanism? They oxidize. Chlorine, microbicidal. I want to highlight sporicidal with a long exposure. Usually can't afford it. In terms of, like, you need to spray concentrated bleach on a table and leave it there for like 30 minutes. It's a bit of a luxury. So, generally disinfection. Okay? Water treatment, you're familiar with that. Iodine. Antiseptic. I wouldn't even use disinfection because you're going to stain the table. So, that's the reason. Am I making sense? And you can see that bleach is very effective against coliform and other enteric organisms. So, like, if you look at this, this is the most concentrated chlorine, which is 0.41 milligram per liter. Okay? It kills them in minutes, less than a minute. Okay, so we're talking seconds. So basically, if you're concerned about the contamination like this, even if you dilute your bleach, you spray it on the counter, you leave it there for 5 minutes, they're all dead. Okay? Alcohols. So, we use 2 alcohols, ethanol and isopropanol. You don't use methanol because it's toxic when ingested, and when people see that the product contains alcohol, they tend to ingest this product. The country where I was born and raised has a long-standing tradition of drinking anything that can be set on fire. I learned how to isolate alcohol from brake fluid when I was 11. I'm not kidding. There is a way. They stopped doing that. They don't add ethanol anymore, but the old ones were ethanol-based. Anyway, mechanism. Disruption of membranes, denaturation of proteins, and desiccation. They suck out water. Level of control, disinfection. What is truly remarkable, though, is this. So I've already highlighted it. So I'm going to highlight something else. Hold on a second. Okay. So, naked, 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 naked. These 4 viruses are naked viruses. I want you to look at the numbers. So the greater the number, the greater the degree of inactivation. Am I making sense? Like the big number means that the virus is gone. If you compare this to the enveloped viruses, such as influenza and Zika, will even appear at some point. Okay. So you have two enveloped viruses. These numbers are, and we're talking orders of magnitude. So 100 to 10,000 times ethanol is more effective against enveloped viruses than against naked. And that is explained by the structure of the envelope. It is composed, in the virus's envelope is composed of phospholipids, and alcohol destroys that layer. In naked viruses, there's no such layer, so they're not affected. Okay? Practical application. If you're in the hospital and you have a patient with common cold, don't use hand sanitizer, wash your hands. If you have a patient with viral gastroenteritis, norovirus, don't use hand sanitizer, wash your hands. Make sense? Questions? Moving on? Okay. Peroxides, that's pretty straightforward. So, oxidation, obviously. You can increase the action by adding acid. Sporclins, it's a peracetic acid shown here, produced by a company located in Metter called Steris. Okay, very good, very sterilizing agent. So toxic that you have to wear a respirator when you work with it. Okay. Vaporized hydrogen peroxide is used. Steris makes vaporizers. It is used to sterilize rooms. Okay, it's a big tank that you move into the room, turn it on, get out of the room, shut the doors, turn off the HVAC. The room is filled with hydrogen peroxide vapors, kills everything. The room's sterile. Does that make sense? Okay, surfactants. So this is the story. We have two types. We have cationic with positively charged active component. Then we have anionic with a negatively charged active component. You can see that both of them have these really, really long tails. Hydrophobic tails, okay? So which one is more effective? If you look at the graphs on the right, so this is for cationic surfactant. This is for anionic surfactant. You can see that cationic surfactant kills bacteria much faster. Just if you look at the graphs. Why? The surface of the membrane in the cells is negatively charged. The positive charge right here, okay, these positive charges, they get attracted to the negatively charged surface. So this and this gets attracted to the negatively charged surface of the membrane, and then this hydrophobic tail gets incorporated, and voila. Membrane is disrupted, bacteria are dead. Anionic surfactants cannot do that. Okay? So they just mechanically remove the stuff. Basically, sanitization or degerming. Okay? While the cationic can disinfect. Your household items, like Lysol, it's cationic surfactant. Okay? Phenols and bisbiguanidins. So phenol, pretty fun chemical right here. The first antiseptic chemical, so-called carbolic acid, that Joseph Lister, 1860s. Extremely toxic, very powerful irritant. The skin was like, those surgeons, their skin was dead on their hands. They act through denaturating proteins and disrupting membranes. And there are some derivatives, for instance, bisphenols. So this is bisphenol, okay, hexachlorophene. They were added to plastic to have antibacterial effect on the drinks like that. Okay, not only individual plastic bottles, but also plastic bottles that you would buy water in, like from Costco, whatever. Okay. Turns out they can leak into the water and disrupt certain endocrine pathways in very small concentrations. They were banned. They don't edit anymore. Nobody died. Nothing changed. So it was excessive in the beginning. Another example of excessiveness, one of my favorites, is triclosan. It's right here. Obviously, don't memorize the structure. So it was a very safe, like seriously, really safe, phenol derivative that was used in hand soaps. You're too young to remember that, but it was happening at some point. And it was a complete disappointment for two reasons. First, in the real life, it was not as effective as it was in the lab. And second, all this enormous amount of triclosan went into the groundwater, right? And when you expose a population of living organisms to a selective pressure, which is triclosan, they evolve and develop what? The R word? Resistance. Practically all environmental bacteria developed eventually resistance to triclosan. And I think in 2018 or maybe earlier, FDA officially just shut the whole thing down. And she said, screw that, we're not using that. Recommendation is to kick it out. You will not find it. It's not used anymore. Okay? Now, this hard to pronounce word, bisbiguanidins. Basically, no one of them. It's chlorhexidine. If you work in the clinical settings regularly, you know that word. Okay, it's very good antiseptic. It's been shown to have the same efficacy as iodine, betadine. But it's safer, less toxic, and can even be used for like bathing newborns and stuff like that. Okay, it's really safe. Now, heavy metals. So I highlighted some of them. I'm going to quickly cover some of these effects. The most important part. So the mechanism. They inhibit enzymes. And in order to inhibit enzymes, you need very small amount. So the term is oligodynamic. It means that they act in a very, very, very small concentration. All right? Good, everybody? Okay. So, let's chat about kind of each and every one of them. Not to the length, but I'm going to highlight whether they're used or not. So, mercury, not anymore. Used to be used in amalgam in the dental practice, but we don't use it. For obvious reasons, it's toxic. Silver. Way too expensive, but this is where the term silverware comes from, right? Because silverware kept food fresh, okay? Same story for gold, but it's even more expensive, okay? Copper, that's for poor people, but it works just as well, okay? Copper was used in ancient times to keep wine and other stuff fresh, because if you use copper vessel, it has strong antimicrobial properties. According to some records from ancient Greece, the antimicrobial properties were discovered when somebody placed copper shavings into the open wound, and initially I was like, why would you do that? And then I realized the swords were made out of bronze, which contains a lot of copper. It was probably bronze shavings. And they were like, somebody just hacked my leg. I need to do something about it. Nothing helps. Why don't I do that? Okay, maybe that was an experiment. Anyway, makes sense. Zinc, most disappointing. So I looked up the studies of all those zinc things against the cold. None of them works. Like good, legitimate, placebo-controlled, double-blinded, randomized. Nope. Zinc, no, doesn't work. Don't waste your money on that. If you have a common cold, if you treat it, you're going to get better in a week. If you don't treat it, you're going to get better in 7 days. That's Russian saying. Now, this is a really cool study. I'm not going to go into details. It's a very, very well done multi-center study. They covered different surfaces in a hospital with a copper. It was extremely expensive because, like, if you have a bed, you can't just come over and spray it with copper. You have to send it to a special facility. It was like thousands and thousands of dollars, but they did it. They showed that. So on the left, that's a graph before the copper, isolation of bacteria from the surfaces. And this is a graph after the copper. So as far as I know, a lot of hospitals now incorporated in the practice. Full disclosure, somebody told me, somebody who worked at the Cleveland Clinic, that clinic started to install kind of copper-coated faucets. I don't know where, no idea, probably in more important like hospital areas, but that would make perfect sense because if you can reduce the number of hospital-associated infections, we're not only talking lives, we're talking billions of dollars in medical bills. Okay? And finally, alkylating agents. These guys, all of them, are extremely toxic. Okay? So, they modify structure of proteins and DNA, which means it changed function. DNA and proteins are not functional, cells die very quickly. Okay? All of them are sterilizing. Okay. Things that I can ask you about this, folks. Well, application, generally. So, for instance, ethylene and propylene oxide. Very convenient to sterilize plastics. It's a gas, it can penetrate everywhere. Okay? Formaldehyde. Gas, fairly cheap, used to sterilize facilities. Pump it in through the HVAC, leave it for a couple of weeks. It will go away eventually, everything inside will be dead. Okay, now, the water solution of formaldehyde, glutaraldehyde, phthalaldehyde, and beta-propione lactone are all liquids. And I want you to know which ones are gases, which ones are liquids. They are used to preserve specimens, either to make sure that the specimen is not infectious anymore or just to preserve it for a long time. Okay? Does that make sense? Okay, so this and this are gases, while these are liquids. Okay? Good? Questions? All right, so we're going to take a break.